Okay, I think we're probably good to start today. Welcome everyone to today's seminar. Today I'm happy to have Dr. Daniel Baker with us. Dan is the director of LASP, the Laboratory for Atmospheric and Space Physics, and is responsible. Probably good to start today. Welcome everyone to today's seminar. Today I'm happy to have. Apologies, the stream just started in the background. Sorry for that. He is responsible for setting and implementing policy regarding scientific, technical, and educational mission at LASP, and has led the largest research institute at CU Boulder since 1994. He also serves in 3 University of Colorado Boulder departments, including astrophysical and planetary sciences, physics, and aerospace engineering. His research focuses in space instrument design, space physics data analysis, and magnetospheric modeling, with a primary research interest in plasma physics, energetic particle phenomena, and planetary magnetospheres, and in their vicinity. In total, Dan has just over 900 refereed papers within the literature. He is a fellow of the American Geophysical Union, the American Institute of Aeronautics and Astronautics, and the American Association for the Advancement of Science. He's a member of the International Academy of Astronautics and the U.S. National Academy of Engineering. Today, I'm delighted to have Dan here with us to talk about solar-terrestrial data science, past experiences, and future prospects. If you'd like to take it away, Dan.
Thank you, Kyle. Thanks for everybody for joining. I'm going to talk today about solar-terrestrial data science with an emphasis on more on past experience probably than the future prospects. But I would like to acknowledge the colleagues who played such an important role over the years in the aspects I'll talk about. Dimitris Vassiliadis, Bob McFerrin, Lee Bargatze, Alex Klimas, who passed away a short while ago. And I should also mention Surya Sharma at the University of Maryland, who passed away recently. They say that stealing from one person is called plagiarism, stealing from many people is called scholarship. This will be a very scholarly talk. This is an outline of the themes I'll talk about, an introductory portion, some of the early work about chaotic particle orbits and the reasoning that led that forward, global magnetospheric dynamics, nonlinear dynamics, detecting modes, the understanding of low dimensional chaos kind of work and how some of this has been applied, and then the promise that this has going forward. We have been very interested, of course, as a group, as a team, in the sort of information era, the science drivers, issues about informatics, managing and accessing large data sets, the availability of higher space and time resolution measurements, rapid response requirements in operational systems, data assimilation into models crossing disciplinary boundaries. All of these things were elements of what we established a number of years ago now during the sort of anniversary celebration of the IGY. There was an ICSU program, an IUGG program that we dubbed the Electronic Geophysical Year. This actually commenced on the, let's say, the 7th hour of the 7th day of the 7th month of the 7th year of this century at a meeting in Perugia. But it certainly was an attempt to recognize just how important data science really was to our field. At about those times, working with Charlie Barton and others, we tried to assess the information that was there, was out and available digitally. And at that time, more than 20,000 petabytes of digital information were estimated to be present in various media. This has probably gone much, much larger now, but this was one of the elements that was considered as to why informatics really should be one of the pillars of modern science, along with experimental observational science, theory, computation. And many consider computation, I suppose, a part of informatics, but in this EOS article, we were distinguishing the acquisition, and the utilization of data as a separate pillar. Arthur C. Clarke wisely noted that information is not knowledge, knowledge is not wisdom, and wisdom is not foresight. I think we all have as our goal to be able to take vast amounts of information and to develop more of a predictive kind of capability to have understanding of what's likely to happen. And each of these elements is separate and distinguishable, and one is not the other. So nonlinear dynamics, this where a lot of our work began back in a long time ago in the 1980s. Nonlinear methods, in general, a term for modeling systems. It can be for plasmas, starting either for physical models, forward modeling, or using data and inverse modeling to understand how the dynamics really works. Some methods are appropriate for plasmas in dynamic equilibrium. Others are appropriate for plasmas that are far from equilibrium. But a large number of methods have been developed for solar wind magnetosphere coupling, solar radiation ionosphere interactions, and so forth. And of course, there are many famous names in mathematics, applied mathematics, that one can point to: Poincaré, Arnold, Lyapunov, and so on. In addition to space plasma physics, these methods have been applied in a lot of other areas. And in fact, the application in other areas are part of what we did, I think, back in the early days to bring to bear on space plasma physics. And the nonlinear methods, I think, are the precursors of modern data science, machine learning. And so we're going to talk more about that in this talk. So some historical snapshots. Poincaré, of course, a very famous name, maybe most notable for his work on three-body problem. But understanding the solvability of nonlinear differential equations, and of course Lorentz and the famous butterfly effect, flapping of wings and butterfly in Asia might lead to a completely different behavior for the atmosphere in North America. The chemist Ilya Prigogine receiving the Nobel Prize for his work on self-organization. All of these people and their thinking influence greatly our thinking about how to address and understand the complex connected Sun-Earth system. There's a lot of work in the 80s trying to understand the stability of the Earth's magnetosphere, magnetotail, and also understand the suddenly instability that occurs during the prototypical, the sort of essential element of instability, the magnetospheric substorm. The Harris sheet was identified as a stable equilibrium, seemed to fit the observations well, but understanding how that system could suddenly go unstable became a topic of considerable interest. There was a study then of the motion of individual ions in the plasma sheet, trying to understand how that might contribute to sudden instability, reconnection, X-line formation. Spicer, Chen Palmadesso, Buchner, all addressed this problem in various ways. And there was a considerable interest in whether, as the plasma sheet thinned sufficiently in the magnetic field, attained a small radius of curvature, whether the particles going into more chaotic kind of orbits might contribute to the instability and lead to the current sheet breaking down. And this was later generalized to more realistic geometries, more large-scale kinetic codes, and so forth. For simple geometries, this provided a likely mechanism, for storage of energy first and then release of that energy. And in fact, some predictions of this kind of particle motion leading to temperature anisotropies was highly regarded as a candidate for giving the kind of temperature anisotropies that might be the source of system instability. However, as one understood the more realistic configurations of the magnetosphere, this was more challenging, I guess, to believe that this was the answer, or at least in its entirety. There are many kinds of physics involved in our discipline, of course, where individual particle motion and sometimes chaotic motion can play a very important role in shock acceleration and certain aspects of radiation belt acceleration, particle scattering in more complicated geometries and so forth. And so these things remain of considerable interest in a variety of ways. Kyle might have wanted me to talk about the entire connected Sun-Earth system. This is a diagram, I think, that comes back way back from our NSF-sponsored work for the CISM program, the Center for Integrated Space Weather Modeling. In fact, I'm going to spend more time here talking about the right side, the coupling of the solar wind to the magnetosphere ionosphere system. This is where I spent a lot of my time working, and so I want to give more emphasis to that aspect of this entire connected system. To do that, let me start just by talking about the elemental kind of dynamical element. I guess that's a better way to say it, the dynamical element of solar wind magnetosphere interaction, the magnetospheric substorm. And so a southward turning of the interplanetary magnetic field leads to enhanced day-side reconnection. This is well understood, well appreciated. That enhanced day-side reconnection loads more energy into the system, allows more energy to enter the system. Many things result from this. The electrojets grow around the entire auroral oval, actually. The entire auroral oval expands, the polar cap size increases, the magnetic field in the tail, the energy content of the tail increases. And so this is all symptomatic of energy storage, tail energy storage associated with this enhanced coupling with the solar wind. And that in turn leads to the near-Earth plasma sheet thinning and enhanced cross-tail current. There are other features like flux dropouts at geostationary orbit and so on that are all symptomatic of this, but they're all basically related to a massive increase in the cross-tail current. And this can be, there can be smaller episodes of energy dissipation, pseudo breakups and so forth that are associated with this. But I would say to qualify for as a real substorm, the entire system goes unstable. There's a massive and rather global instability of the entire system. And this is the substorm expansion phase. And as some of you know, I separate the world into two classes of people, leaf inspectors and forest rangers. I tend to be more in the forest ranger camp most of the time. But it was very striking to think about just how remarkable it is that this massive plasma system, the magnetosphere, ionosphere system, can be in a rather stable initial state, a ground state. And with the addition of energy can grow in its tendency toward instability and then can go massively unstable for the entire system. I was very taken by the analogy of my late friend Ed Hones, who drew this analogy just to try to explain the formation of plasmoids, the release of a lot of energy, the dumping of energy from the tail. And he analogized that the plasmoid formation, reconnection in the near-Earth region, pinching off a lot of the plasma sheet is like a leaky faucet. And this was very much on my mind when we were trying to study how to sort of characterize this using more global kind of parameters. A very much used much cited paper with Lee Bargatze, Bob McFerrin, Ed Hones, and myself, put together a data set. We regarded that an index, a global index of instability of the magnetosphere, the AL index, the Auroral Electrodet index, might be used for this purpose and had been used a lot in studies. And the interplanetary electric field thought to drive this kind of magnetospheric behavior, VB South. And so in order to study the evolution of this from weak to strong activity, we put together the data set. Bargatze really did most of the work, put together individual segments from quiet to quiet intervals, 30 intervals were put together, and formed a time series that was very useful for various kinds of studies that we wanted to do. And so arranging it this way produced the Bargatze data set, which a lot of people use, but here's the response, and here's the putative driver for that in the lower panel. So working with Bob McFerrin, Lee, and others, we really wanted to use a very powerful method frequently used in engineering, which is linear prediction filter analysis. Vesting all of this complex behavior in this vast and complex system as a filter element, and taking the electric field as input and the AL as output, and trying to characterize the filter response that captures all of that dynamics. And that work led to this kind of stacked set of filters going from weakest to strongest behavior. And the time lag in hours is shown down here, the impulse response function stacked from the weakest to the strongest activity according to this formulation. And what we found was that there was a shorter peak in the filter element, and we attributed this to the driven part of the system. And there was a second peak that appeared at least at weak and moderate activity levels that was attributed more to the storage and release of energy from the magnetotail, the kind of reconnection driven substorm. So the bimodal response, again, that work was, I think, looked to by a lot of people as demonstrating that indeed there's a growth phase response that occurs rather promptly, and then a longer, typically an hour-long kind of storage phase, and then the explosive release of that energy. But as one went from moderate activity to strong activity, that second peak tended to diminish, and this was also suggested that the magnetosphere becomes more directly driven as one goes to the stronger activity. This became a very intriguing idea, and I read the book by Gleich and a lot of the papers that were cited in it, especially the paper or the article by Shaw. And so we tried to develop and did develop a model, the drippy faucet analogy. And the idea of this is that taking this drippy faucet, but making it more of a mechanical analog, a mass on a spring, and adding mass continuously to this. When the spring reaches a critical distension, a piece of the mass breaks off, and that's like the drippy faucet. And how fast this spring is moving past the critical distension determines how much the mass is released, and this became the drippy faucet kind of model of substorms. This was later extended by Klimas et al. To be more magnetic in character, magnetic loop and magnetic flux rather than mass, but basically the same picture. So to sort of recap the thinking that went on in these early days, the plasma energetic particle magnetic field data provided this view of global configuration and reconfiguration. The drippy faucet model, a storage release model, was put on more firm ground, I suppose you could say. There were a lot of variants thinking about different natures of the instabilities, thermal catastrophe, and as I say, the low magnetic flux picture. And the University of Texas group also developed this, replacing more of the magnetic phenomenology with an MHD and kind of dissipation physics in the WinMe model. I won't dwell on this other than say that this was developed more extensively and actually was put into the CCMC, still there, as to my knowledge, and can be used for modeling the global system, should one wish to do that. Now, taking a tack that spun off from this, I guess, is thinking about the low dimensional, or understanding whether there might be a low dimensional component to the plasma systems that we study. The plasmas, of course, can be characterized by oscillations and waves in near equilibrium. But when they're out of equilibrium, there can be many different modes, almost infinite number of modes. Question was whether one could really, as the earlier linear filter analysis suggested, whether there might be some particularly strongly coupled modes, or whether this might be a system you could characterize as low dimensional and almost chaotic in character. And some of the early methods to look for strongly coupled modes by Vasiliadis, Shan, and so on were hopeful and suggestive, but they were imprecise and sometimes returned spurious results. More appropriate methods were based on input-output models, again, going back to filter analyses and neural network kind of approaches. And this work and extensions with other kinds of methods to detect modes, the wavelet transforms, and different types of spectral mode analyses, orthogonal functions, principal component analyses, and so on, continue to suggest that in many ways one could think of the magnetosphere, the solar wind magnetosphere ionosphere interaction as being a system that has some dominant modes and mode coupling that really lead to the ultimate responses. For more practical purposes, we went back to or utilized in parallel linear prediction filtering to get some sort of operational or practical results out of this work. We, of course, had done this with substorms in the 85 paper with Bargatze. The guy took the linear prediction filter approach to specifying geosynchronous electron fluxes with Kp as the driver. And in 1990, we published a paper using linear prediction filter method using the solar wind speed and the fluxes at geosynchronous orbit, and extended that to all L values, essentially, with SAMPEX. So the filter analyses led to this kind of picture for a moving average linear filter. Describe the system's response as notes here for SAMPEX or for any geostationary spacecraft. Typically at the zero epoch time, there's a diminution of the flux. There then is, on a couple of day time scale, a rise to a higher flux level, and then this decays away and goes back to its kind of initial level. So this is sort of the picture of how the magnetosphere, through all of its complexities, processes solar wind driving and ultimately leads to an enhancement of the radiation belt properties. So in principle, again, going back to early work with CISM, Center for Integrated Space Weather Modeling, one could go back to the sun. One could use Wang-Chili RG Enlil model to specify, 2 or 3 days in advance what the solar wind was going to be at Earth, convolve that solar wind speed with the linear filter and predict many days in advance what the radiation belt population is going to be like. And so this work really was the basis for the relativistic electron forecast model, which, again, to my knowledge, is still in use. Sorry, it's still in use at the Space Weather Prediction Center, and it is used to take solar wind data, convolve with the filter that I showed, and predict the fluxes of energetic particles at geostationary orbit. More generally, we took the measurements from the SAMPEX spacecraft and looked across all L values, as shown here, came up with sort of a picture of what you might say, the global model, global filter picture really was. And there were several things that were evident, is that there was a mode, term P1 in this early work, that was really associated with high-speed solar wind streams, enhancements of the electrons throughout the outer radiation belt, and a second mode that was more prompt, almost immediate, and extended to lower L's typically, and very, very rapid enhancement. The P1 mode was really associated, let's say, with with CIRs, correlating interaction regions, and enhanced diffusion, while the P0 kind of mode was interpreted to be more associated with CMEs, magnetic clouds hitting the magnetosphere. And then a key part of this was also this decrease in flux, the third element here, the V1, which was a rapid decrease of the particle flux as the driver hit the magnetosphere. So this work, again, proved to be of pretty significant use for understanding radiation belt behavior. Further work was done with graduate student Josh Rigler here, using more recursive state model, mode estimation, and this really just means that one takes the predictions and sort of feeds them back into the input, so one's getting a recursive kind of a filter rather than a simple linear filter. And so how does one achieve some useful and predictive things? Well, filters or things related to filters seem to be very beneficial for a lot of different purposes. For the geostationary orbit, we've talked about that. Relativistic electron forecasts at geostationary, more broadly throughout the magnetosphere, again with SAMPEX and Polar, that proved to be very effective. Magnetic field model predictions, nearest neighbor kind of data mining, all I think grew out of this kind of thinking. Field line currents, and many other things that one could point to. Related to this in a way was the attempts to do data assimilation, nudging of the basic models toward better results. And this is work with Dan Moore and his graduate work, but taking the output and trying to minimize the error. And so having a basic model specifying things at a point, and then looking at past examples for those kind of driving conditions, and then nudging the model more toward the proper state by looking at what's essentially nearest neighbor kind of behavior in the past. And this whole line of thinking of state space analysis, again, I think proved to be very powerful. That the top just recognizes that there could be a relationship between some input U, whatever that might be, and some state variable that you might characterize the system at being at a particular state in energy content or magnetic configuration or something like that. And that in general, this would not be linear. that there might be some nonlinear kind of behavior as characterized by this curve, but one could use a local linear approximation to use a lot of these methods developed in order to make forecasts over some broad range. But what was really intriguing was to think about the nearest neighbor state space trajectory, that if there is a trajectory in state space and one can go back in the data record and find all the ones that are close to that same kind of behavior driving over time, that this could lead to powerful forecast methods. That's in essence, I'd say, what the more work was, and the work of others, Vasiliadis and so forth. There were even attempts to use this state space thinking to have a state variable and to understand how one might have a relaxed configuration that the system is trying to get to, you might say, having recognizing that one can drive this to a very stressed configuration that just grows and grows in stress level, and then catastrophically transitions to the relaxed state. And this led a lot of people, including our group, to think about sand pile models and things like that, self-organized criticality. But the idea of this is that wind blowing across a sand dune might lead to buildup of this kind of a lip, and that reaches a point where it just goes globally and catastrophically unstable and releases a lot of the material that's built up in this loading process. So sand pile models, notably Sandra Chapman and her colleagues, worked on this as an aspect of loading-unloading system, that there could be some threshold instability, a local phenomenon that would be dependent on the local state, some local gradient or so. But the criticality would be that there's a global state on the verge of instability essentially everywhere, and the system self-organized toward this limiting critical state, which seems plausible for the magnetic tail. Criticality produces a stable global configuration until there's an avalanche, and there's a real sensitivity to external disturbances in this way of thinking. And so self-organization was very much on people's minds, decades ago, the concept of self-organization, that nonlinear systems, chemical systems, convective flow, and so forth, that the interactions are shaped by complex multiple feedbacks, positive ones that amplify the dynamics, the emerging dynamics, the negative ones that modulate, constrain them. And a lot of the work that I've reviewed here, I think, could be thought of as an expression of this kind of self-organization. Thinking again about whether there's evidence from the data in this kind of behavior, I think there was. And just looking at the evolution from a global auroral imaging of the appearance of a spot on auroral brightening, growing in size, and then suddenly exploding to cover much of the sky. The associated with fast flow in the tail really suggested that this was worth examining more in terms of an avalanche instability. Uritsky and coworkers developed this kind of thinking quite extensively. Did quite a remarkable job of looking at many individual auroral substorm imaging elements, and did the statistics on this, and each avalanche being tracked from the beginning to the end, and in the ultraviolet image analysis suggested that since this was following a power law, was sort of scale-free, that this was indeed evidence of a self-organized state, something like a self-organized state in the plasma sheet that was leading to this auroral brightening and explosive release of the energy. So again, to review the bidding here, a lot of work led to the subsequent work in the 90s and early 2000s, I would say. But recognizing that this is an input-output system, that one can analyze the solar wind drivers and many responses in those terms. That as the system goes from its quiet behavior to more disturbed behavior, there can be smaller releases. The dripping faucet model suggested that there could be an evolution from simple drips to period doubling, drip, drip kind of thing, to essentially chaotic behavior as one drove it strongly enough. And this was evidence of nonlinear behavior of the connected system. I'd say a lot of these methods proved to be very effective and allowed for prediction using filter methods. But there was also a lot of criticism leveled at this work at that time that yes, these are successful at predicting, but they're really not they're not revealing what the underlying physics is, and therefore this work was in some cases disparaged, or certainly was not embraced by many people, because there simply wasn't enough understanding of the black boxes, you might say, that this seemed to represent. But I really would say that this, starting with some people reading the literature about chaos, low dimensional systems, chaos dynamics, nonlinear dynamics, I think led to a lot of immensely useful work and a lot of immensely useful insights into how the system we study is not just about local plasma physics, but it's really about the global system. So I would assert, as did Klimas back in 2000, that there's some fundamentals about magnetospheric or magnetotail dynamics that bear paying attention to, that this is really a spatially distributed loading unloading system. Magnetic flux is the relative conserved quantity. There are threshold instabilities, be they current-driven or tearing or whatever, that leads to localized reconnection. But the system is at a critical or nearly critical state, that there's localized reconnection, broadly distributed, can indicate that the system goes unstable, essentially in a global way, and that these analyses in terms of scale-free avalanche kind of distributions and so on really are consistent with that kind of a picture. And so I'd say nonlinear dynamics, complexity as manifested in all these studies, really does indicate that the magnetosphere as a nonlinear system can be very sensitive to initial conditions. The output's not necessarily proportional to the immediate near-term input. There are often feedbacks that the output can feedback and influence how effectively it can be input to the system, can exhibit what seems to be random behavior, but it can really be a manifestation of low-dimensional behavior, deterministic chaos. And nonlinearity can give rise to the self-organization, order emerging from this chaos system going to a completely different state. There can be randomness and apparent order in a single system, as many other disciplines have shown, and there can be different types of systems interacting strongly. So a diagram that's been modified only slightly from an earlier paper, but there's 40 years of nonlinear thinking. I guess one could say that this was probably stimulated by the analogy from Hones and a lot of work back in the 80s, 90s, early 2000s. And now, of course, exquisite measurements being made with magnetospheric multiscale about the reconnection process itself, and understanding how this works on the very microscopic level, but also understanding how the microscopic behavior contributes to the very global kind of behavior of the connected system. And it really is remarkable. And we have this wonderful laboratory in our immediate neighborhood that we can study. So I would say again that I don't know, this up here is sort of blocking my view, but you know, feed forward artificial neural nets with back propagation. This work also extends back into the 1990s. This now has these are the workhorse today of the methods that are so much in vogue and so extensively utilized. But there's quite a literature about applying these methods early on to geomagnetic indices, to relativistic electrons, again, to the total electron content, spacecraft anomalies, all kinds of things. And so I think the disparagement I was talking about before was unwarranted, and these methods are proving to be very successful. But the utilization of supervised and unsupervised artificial neural nets now is at the core of a lot of the machine learning techniques that I won't even attempt to review here, but I think, again, one can point back to the work on geomagnetic indices, support vector machines, or support network, support vector networks, and self-organizing maps, and all the stuff that has been studied so extensively is leading to better, just clearly better kind of forecasting methods. To get a perspective on this, as far as from the machine learning perspective, I suggest you read Comporiali's recent reviews. So just some remarks, I guess I've seen quoted in various places on machine learning. Artificial intelligence is no match for natural stupidity. In data science, 80% of the time is spent preparing data, 20% of the time is spent complaining about preparing data. I think we can all stand by that. Don't be intimidated by jargon. Again, I'd say that that's true. A model is just a fancy word for a recipe. Don't hate machine learning for being simple. Levers are simple too, but they can move the world. And I think that there's more realization now that these methods that can be so successful and can reveal so much through data mining and machine learning really are very worthwhile to get the results we need. And I would just leave you with, if you had facts, you wouldn't need statistics. So the outlook, I'd say space missions and ground instruments, will continue to increase in their capabilities, returning huge volumes of data. The nonlinear methods that we talked about here will probably keep increasing in applicability, maybe in complexity, certainly in data mining capabilities, and probably in forecasting. The data conditioning, they're certainly useful for that purpose. The empirical model development is immensely powerful in my view. Data assimilation, very powerful. Prediction, very powerful. And the filter, neural net, other methods are just going to increase in importance, no matter what name they have. So just to wrap this up, I would say that the advent of suitable computers in the 80s allowed mathematicians, of course, to solve many problems that seemed unsolvable decades ago. Fractal geometry, nonlinear dynamics, chaos, wavelet, other transform analyses, neural nets, and so on were formulated to be an adjunct to the traditional linear and spectral approaches. And I think gave a lot of insight. And I'm immensely grateful for Blake's book and being able to get to work with a group like with Alex Klimas and Dimitris Vassiliadis and Bob McFerrin to pursue these things. I think these in the 90s, these capabilities produced a lot of the methods and some for an analysis of data and some for simulation, improved simulation methods. While several methods found limited use and didn't develop further, others have found immense applicability in large data volumes and generating empirical models. And I think that's crucially important. So with that, I'll say thank you, and be happy to answer any questions. So, anybody there?
Yep. Sorry, just starting my camera. Thank you for a wonderful talk, Dan. That was really nice to see kind of that history of data analysis. I quite liked your quotes. I think those are good to put things in perspective. And you did mention some of the disparaging comments or kind of attitude you received towards some of this. Do you feel like that is now going away, or do you feel like we just have more people are using it? Do you feel like that attitude still sort of exists, or are we actually moving away from it and gaining more acceptance in these?
Yeah, I think machine learning, artificial intelligence, and so on have become in vogue, and so I think there's more acceptance that these methods, which have applicability and produce results, are okay. I think there's also enough work going on to look at the inner workings of neural nets and stuff, and defining more what's going on physically. That it's less it's less just a black box with no understanding emerging from it. But as you can tell, I'm a little irked that this work was shunned a bit back in earlier times, because I think there were a lot of paths that could have been pursued more thoroughly, more aggressively, and perhaps we could have been money ahead had that been more accepted at the time.
Yeah, unfortunately, it seems, I think in our field more than others, it takes a lot of time for new
Yeah,
ideas to gain traction and acceptance to start pushing them forward.
yeah, I think
Um,
that's right.
yeah.
Yeah,
So you also focused or pointed towards MMS and the microphysics. A lot of what seems to be in the field now is moving towards macro scale concepts and macro physics. I think these tools will still be helpful in that.
yeah,
But how do
yeah.
you envision addressing that? The microscopic was easy, well, not easy, but was capable with something like MMS. But to do the macroscopic version of that, would you envision something like imaging or constellations of satellites in
Yeah.
order to kind of address the same problem?
I guess given our penchant for wanting to measure the plasma physical properties, probably constellations, using uh, multiple ones, dozens, or maybe even many dozens of spacecraft, and getting adequate measurements over some mesoscale region might be the most productive and accepted kind of way to go next. Um, but as I said before, as a person who separates the world into the leaf inspectors and the forest rangers, I think we have to bring those two ways of thinking more together, and the combination of remote sensing and constellations to give mesoscale measurements, I think, is the missing piece of this. I personally feel that we have a rather good handle on the global, and now with MMS have remarkable insight into, on the very micro scale, on the electron scale, how reconnection really works. But we've got to fill in the holes in between.
Mhm.
Yeah.
Cool. So Hugh has his hand up, and
Yeah.
I'll ask him to unmute to ask a question if he's able to.
Okay. Hi, Hugh. Are you there, Hugh?
Hello, hello. I was taken aback. I didn't unmute. Anyway, so hello, Dan. Thank you
Hi.
very much. Very nice. And I, from the forest ranger point of view, I would like to bring up again the idea of the analogies that might exist between solar flares and and magnetic disturbances like storms and substorms in
Yeah.
particular.
Yeah.
So there's a new discovery, and I'm going to sound my own horn here because I'll put the link online. Actually, there is a new phenomenon that's been recognized in solar flares that anticipates the occurrence of a flare, right? So it's a new global property that people had not really recognized before, and the property is the growth of hot, dense corona before the flare actually happens. And it enables one to predict the occurrence of a flare by 10 or 15 minutes or 30 minutes if you are lucky, or if it's a big flare. And so right now, there is no literature on this. It's a new phenomenon. I call it the hot onset precursor event, because that's an acronym. It's HOPE. It's so you can, and I developed it because of the rockets that just were launched at Poker to try to catch a solar flare, and they succeeded. All right, and so the method I have actually anticipates when a flare is going to happen, so it tells you when to push the button on the rocket launch. I don't know if they used my method, but it would have worked. So anyway, so the thing is, the physics of it is, from the forest ranger point of view, there is this inflation of an active region, I think, kind of analogous to the inflation of the geotail prior to its catastrophic energy release. And the distinction is, of course, that in the case of the geotail, you have the solar wind.
Right.
In the sun, you don't. There is no solar wind. And so the driving of this cross-tail electrostatic potential difference, which is crucial to the substorm, has not been really described in the solar case.
Yeah.
So anyway,
what you say sounds very plausible, and as you say, unfortunately for remote systems like the sun surface and so on, one can't really get that handle on what the building up driver is really doing as well. And
doesn't imaging, I mean, this is the question, right? So you want to envision the global system. You want to. I mean, I loved your bullet there about who needs statistics when you've got facts. I mean, you can get hints of what's happening through the statistics, but really there is a physical mechanism that we want to winnow out.
Yeah, I've heard some of our solar folks talking about the work you're citing, Hugh. I haven't seen the papers or anything. I guess you say there aren't any quite yet, but I would really look forward to that. And I think it is probably analogous to the magnetospheric system, which we can treat more as we can observe the driving as well as the response a little more in situ, a lot more in situ. And that, I think, is what makes this laboratory in our own neighborhood, our own backyard, so useful for understanding this as a general example of a plasma loading unloading system.
So if there's time, I could show a screen on how well this HOPE anticipator works.
Well, Kyle is the boss here, so he can see what's possible, I think.
Yeah, why don't you let me close up the stream, and then we can discuss a little bit more if Dan has time. So thank you everyone for attending. Our next talk will be next Monday, and Dan Billett will be discussing exploring the thermospheric response to high latitude magnetosphere ionosphere driving, impacts, consequences, and exploding satellites. So I hope to see everyone next week, and for those that would like to stay, you are